It's time to go over all the things we've learned so far. To do any kind of programming in Stationeers, you will need the IC10 microchip. To run the chip, you either need the circuit housing or one of the atmospheric devices, which can also house a chip. To program the chip, you will need a computer, either stationary or handheld, and an IC editor motherboard. The laptop can be taken anywhere, but to program something that is running somewhere, you first need to get the chip from there, plug it in the laptop, do your programming or export your program and put it back. But you can never be mistaken about which target device you're choosing. It will always be the laptop. The stationary computer, however, can select all the connected devices and can program directly to them, can directly export, and then it will immediately be working. But you might be confused about what's selected here, which may change if you place a new device in the world or if you load your save game. So that's a trap. Personally, I prefer the stationary computer because I want to do quick changes to my source code and immediately see the result. To control a device with logic, you need to not only connect its power, but definitely also its logic connector. Many devices have those combined, so if there's only one connector, that's for power and logic, always. But if there's two, well, if this one's not connected, then there's no use debugging your program, it cannot work. The values you can program can be found in the Stationpedia. Here the filtration device has all of these values which can only be read, but we also have, for example, the open-close value which I'm using here. This could be used to signal to you that one of the filters is down, or you can use a speaker, whatever floats your boat. While we're at this device, when you normally build these and don't program them, their mode will be 1. So if you turn them on, they will be running. They will be filtering, for example. If you switch this mode to 0, then they will not be running, but they are powered. This is necessary, for example, if you're running a microchip in there, because if you think this thing has filtered enough, it's time to stop the filtration process, you cannot really turn it off with a chip. I mean, you can, but then the program has ended. It can no longer run. There's no more power. But if you instead set the mode to idle, then the device will stop doing stuff, but it will still be powered. So that's the way to go. The programming screen allows you to choose the device where the chip is housed, and then you can say, I want to import whatever's on the chip. You will see that then on the screen. And here you have the proper editor. You can copy the entire source code to a clipboard and paste the entire source code from the clipboard, so you can use external editors, which is sometimes very useful. This editor is very limited, but it's pretty cool for an editor in a game. The filtration device is currently off. Let's turn it on with source code. Now it's on. The program was run one time and then it was over. So if I turn this off now, it stays off. But if I add this line here, we will jump back to 2, so it will be turned on the whole time. See? Instead of fixed line numbers, you should use labels, because if your source code moves around, these fixed line numbers would be a catastrophe to debug. Now, when you have some kind of main loop like this, which most programs that we do in Stationeers probably have, then you should use the yield statement. Your source code is executed in the context of a game. You shouldn't forget that. And so the game has to make room that it has enough time for its simulation. So when it has executed, I don't know, 128 lines with statements, it will force a pause. You don't know when that will be. But if you do this, then you're saying, I'm pausing willingly here, game. So you don't need to force a pause yourself. And I know where that pause will be. So always have a yield in your loop. Usually that's right after the start marker. Not always, but usually. See, it's equally insistent. This little pause that we have that didn't change anything. Particularly since we already experienced the pause here before. The game forced one. So use the yield statement. But how do we address devices? After all, we want to choose one and then say do something with them. Something's supposed to happen. One way is to just choose the device here on the housing with one of the screws. Use the screwdriver. then we can just address this in the source code like this, with D0 for the first screw, D1 for the second screw, so that's it for the filtration unit, for example, and up to D5 for the housing. By the way, you're seeing here that I'm using alias. This just makes my source code more readable. I could, or and still can, use D0 here directly. Downside of this direct addressing here with the screwdriver is something you may already have experienced when tampering with your airlocks. You build an airlock that works, then for whatever reason you rebuild one of the active vents that are in use there, and suddenly your airlock no longer works. That's because every device, everything that you build on the world has its unique identifier. And when I select something here, this is then referring to the thing with your unique identifier. Case in point, you see the name filtration here. If I rename this thing, then you will see that name here also. So it was not referred to by the name, because then how would it know now that the name is different? It was referring to the thing by its reference ID. If I would rebuild this filtration unit, this would no longer work and the chip would throw an error. Instead of using the screws, you can also address a device directly by reference ID, which is what the screws are also doing themselves, but then you're not bound to 6 screws. You can use as many as you want. Here, the reference ID, 1601, or instead you can write $641. This device configuration cartridge might be removed from the game at some point, they keep saying, but anyway, currently you can still use this thing to find out what the reference ID is. For reference IDs, you need to use a different command. S writes to the screws, and SD writes directly. This will become very important later, because some devices can only be addressed with some write directly commands. For example, the manufacturers. You can say, hey, toss out all the gold, or you can say to a logic sorter, filter the potatoes to the left and the other thing to the right. And for that you will need the write direct commands, so that's important. Let's see what happens. Write directly to this device on 0. I'm changing the source code here to behave differently so that I can be sure that my program indeed does what I want it to do. It's turning on and off. Yeah, because I selected the wrong target. Really, keep an eye out on this one when you click export. Now it's off. I cannot really turn it on. So the program was changed. The writing directly by reference ID did work. But it has the same problem as the screws. If I would replace that device, that would no longer work. The reference ID would be wrong. And it's a bit cumbersome to work with these. So what else can we do for addressing wise? Well, there's a third solution, which has a fourth solution bound to it. The third solution is to say, I want to write to all the devices of a certain type. And the fourth solution is to then also filter it down by name. So, structure filtration. How do I know this? By looking in the Stationpedia. Here you can see prefab name is this, structure filtration. I can also just copy the prefab hash, which is actually what the computer uses. Click, copies to click. Currently it's being forced on. Let's replace this here with the number and say off. Does it work? It does. See, the number and the name is the same thing, except the computer cannot work with the name, so you have to use the hash statement around this thing. Then it works. The named approach, though, is very important. Currently, we're writing to all the wall lights to be on. So, if I want to turn only one on or only one off, that doesn't work. But I can use the named approach. The light. This is, though, the SBN command. Here you also have the additional parameter of the name. Now I'm addressing all the lights that have this name. So if multiple lights have this name, then that would have the appropriate effect. Off, off. This one will stay on, off, off, off. See, we're only addressing this one light right now. And that's the way I use it in most programs that I write. You have already seen the alias statement, where I can say I want to give a screw a certain name, so I can address the screw, whatever it's addressing, whatever it's referring to, by using this name, or still the screw name. We also have registers from R0 to R15, and we can use those directly, or can also use a name for those. with the alias statement. But what I want to do now is I want to use the define statement, because instead of writing this in every single line, I can also put them up here. This is equivalent to what we have before. I'm saying all of this type with this name. And here I can use my own names in the source code. That might make it easier. No error. Still working. Some funny dude locked this door. Now he can't get out. Imagine him being such a room without any tools or ability to program. So let's open this door with programming. So let's just select the door and copy the number or the name and then hash it. But of course, no, that's wrong. You have to pick the right door. We use the kit door to make this, right? So let's use this then. No, that doesn't fly. You must make sure that you use the structure. The item kit door is the thing with which you built this. It is not the door itself. This cannot work. Okay, let's pick the door then. Wrong door. You have to pick the right door, which is the glass door. And then we can just say write batch to all the glass doors on the current cable network, open. Escape to Earth. Most devices also have a lock value. That's what I used here. I just said lock 1, and since then the door can no longer be controlled manually. This can sometimes be meaningful. For example, the pipe analyzer, with which you can find out whether there's still pressure on a pipe or what's in there, its values are very important to your program, right? And that's why I normally do this. I say first lock the thing and then turn it on in this order, just to make sure that no one maybe turned it off right after the on statement fired, and then the lock statement comes just when the thing has been turned off manually. First I lock it, and then I change its state to what I want it and stay it to be. Not every value is writable, but most values, I think all values, are readable. So we can use whether the door is open, for example, to turn it on and off our lights. For example, you could tie that to your inner or outer airlock door to save a lot of power in your station, though I think an occupancy sensor might make more sense. We're programmers. What do we want to do? Well, the goal is, whenever I open or close the door, the lights should turn on or off. Whenever means the chip needs to keep doing it. Okay. So much is clear. Then I want to react to the door. I can use the screws or the reference ID like I showed, but I think it's most convenient to just use these names because, structure, glass, door, you don't even have to learn that, you just need to learn the structure. Since I don't want this to happen via any door that may be connected to the current cable network, after all, maybe I put another in and then it would do that too, and maybe I don't want that, I will use the named approach. So I give this thing a name, and here I'm using the name and turning it into a number. As you already know, this statement would open the door. Write batch, as in to all of this type, named, only if they have this name, open 1. The opposite of this is the LBN statement, load batch named, and similarly load batch, and also load directly from R0, load directly from D0, from screw 0, for example. And here we can see what values are needed for this command to be complete. We are loading a value, and the program wants to know where do you want to put that value. Similarly, when you say SBN, the program wants to know where to write the value. We're saying here to that device, here to that screw, and loading to that register. Then we place the type reference. We could also use the number that we've seen in the Stationpedia or the hashed version here. And then we place the name. And then it wants to know the logic type. What is that we want to read? Open we want to read. And now batch mode. See, if you want to write batch, that's easy. You write 1 to the openness of all doors. Then they're all open. But when you load something, then one door might be open, one door might be closed. What is the computer supposed to give you now in R0? This needs to be clarified, man. And that's what you do here. You say minimum, which means that if there are 3 open doors, where open is 1, and one of them and there's one closed door, which will be open 0, then the value that you get here is 0, because the lowest value of all the values that you get with this one statement will be 0. Then we have maximum, and then we have average, and then we have sum, which is what I always use. It's very short, and if I only want to address one device, then, well, this will probably lead to an outcome that is bad, that will not work at all if there are multiple devices that match this this pattern. If I'm saying load from only a certain type, or load from a type that has this name, this might still address multiple devices, you know. But if I plan on it to only address one device, and I use sum here, then I will get values that basically don't make sense oftentimes, and this might lead to the most likely such outcome, and also one that is most easily decipherable in its behavior. That's why I use sum. So if you don't want to read multiple, but you're using the batch named read command because that's the only way to do this, except if you want to use reference ID or screws, then I opt to always use sum. So now we have the logic statement 1 or 0 here in R0. Remember, if you would be using here average, then R0 would be something in between, probably, depending on how many doors are connected. I believe that logic statements work like this. If the value is 0, this is false, of course, that's definitely so. If the value is 1, then that's true, that's definitely so. Values above 1 also count as true, and I believe that any value below 1, like 0.999, counts as false. I don't know what about negative values. For example, minus 0.0001, will this still be a 0? And minus 1 will then count as true? I don't know, I didn't test this. Anyway, now here we have a 1 or a 0, and then I can say all the lights, right batch, not right batch named, all the lights shall be on with this value. So when we come home, we open the door, we get in, close the door, and then everything is dark. Oops, that's the wrong way. So we need to flip this value. How can this be done? Well, you might think, oh, there's probably a comparison statement, and then you compare. If it's 0, then you make it 1, and if it's 1, then you make it 0. But there's a simpler way of doing this. See, the S statement has another variation, actually multiple. We can do this, for example, which means greater than or equal, or less than or equal, or not equal. All of this can be looked up here. And I'm now saying if R0 is equal to 0, R0 equal to 0, then the outcome is true. And true means 1. This write statement, like the others, first wants to know where to write. I'm writing into a register. This happens to be the same I already have. That doesn't matter because I don't need the old value anymore in this case here. So I'm saying if the door is currently open or closed, let's say it's closed. If R0 is 0, if it's equal to 0, that is so, yes? Okay, well then that's true. And true means 1. So R0 becomes 1 if it was 0. And if this is already 1, then it is not 0. Not 0 means then false. So it means 0. So 1 becomes 0, 0 becomes 1. SEQ. And you can make that even shorter because many commands that compare have also a 0 variation. That's really just for particularly 0. Some background, the reason that this existed, because this kind of language is actually quite old, assembly language, is that all of this information needs to be sent to the processor. And when you also have this parameter 0, then you need to send the 0 to the processor, which wastes some cycles. And if you want to really be fast, well, the special case 0 occurs often, and so if the statement itself already has this within itself, that's less information to be sent to the processor. Anyway, if you write SEQZ, then you're inverting this value. So now the lights should turn on. And they do. So we come home, close the door, and then we do stuff. This is a very elegant way of flipping the lights, but let's use a more elaborate, unnecessary one so I can teach you something. Or rather, you have seen the rest of the series, yes? I'm just repeating myself here, man. So almost the same as before. We're getting the value of whether the door is open. And now I made some little sub-programs here. Turn lights on, SB light on. Turn lights off, SB light on 0. On 1, on 0. And then I'm jumping back to start. Now we have to decide where we want to jump. And similar to this command, which compares to 0, we can not just set a logic value, we can also branch. I can say branch if equal to 0, turn lights on. And branch if not equal to 0, turn lights off. This is of course ridiculous, but I will talk more on this. Not sure if the program kicked, so let's just flip it around then. Not equal, equal. Aha, it turned off. So yes, the program is indeed active. The way I did this here doesn't really make sense, because the only alternative to this being executed is that it is not so. And then why not just jump here directly? And this means then I jump down here to lights off, and then I jump back to start. So I don't need this. See, that's a more clean way to do it. But there's an even more clean way, which you should learn, because it is very powerful. I set there 16 registers from R0 to R15, but that's not true. There are two more registers. There's RA and SP. SP is the stack pointer. I haven't talked about this at all yet. RA is return address. And that's just a register that holds basically a line number. And here I'm saying jump to that line number. But what value is written in there? Well, there are some AL statements. For example, I can say JAL. Then I jump to some kind of subroutine. And when I am in that subroutine, for example this one, when this one has completed and I say jump RA, it will jump back to right here, right to the next spot, and will execute whatever is here. Or will continue here when the line is empty. Anyway, and then I can call this multiple times in my source code, and every time this will not return to start or to a decided point, but to where it has been called. So I can say do this, then I do this again, very convenient. Jump RA. And these are AL commands. And these exist also for this logical branching. We have seen already branch equal or branch not equal if 0. We can also do this if you wish. It's the same thing. And then I just add AL. So when you look at it like this very long list of commands that exists is actually not that long, because lots of it is just bloated, so to speak. So let's see if this works. Oh, it does. Okay. What does it do then? It checks if the light should be turned on, then jumps down here and returns here, and then it will also check if the lines are to be turned off, then it executes this, returns here, and then whatever else might be here in this program. I mean, the program might be longer. Of course, the way I implemented this here is useless. Why would I do it this way? The original way, with the bit flipping, where I inverted the value, that was the best way to implement this particular use case. Why would anyone call the same subroutine multiple times? Maybe because you're possibly using some values in there. Here I'm setting a value into R0, we know already, from the door. And then I'm just saying call the subroutine set lights. Then we hit the subroutine, and here we're making use of this register. So whatever's in this register, the subroutine will do it. So this can then make sense to use the subroutine multiple times. For example, here, I just said jump to set lights and then jump to set lights again. And before I did so, I set the value to R0. Move is a statement that just writes an absolute value into a register. Move R0 1, now it's 1. Set the lights, so turn the lights on, return here. Then wait for a short bit. You can also say sleep, but you can also only sleep for full seconds, I believe. Or does this also work? I guess it will be rounded. Anyway, sleep 1 second, 2 seconds, 3 seconds. Yield will only wait for one game step, which is half a second. So this yield statement, like that I explained earlier, you can also just use it for waiting. It's legitimate, it's not a problem. So I'm setting value 1, set the lights, wait, setting value 0, set the lights. That's the concept of subroutines. You're probably familiar with the sorters, which can be programmed with the heinous crime that is the sorter motherboard. And these are the logic values. You can only program that with IC10. But more interestingly, there's also the logic sorter. So instead of programming that thing directly, you can program this thing to behave in a certain way. So that's a new thing for a few months now. You can write into this device some statements. You can say filter if something is equal or is not equal, filter slot, and so forth and so forth. In the same way that since then you could be doing that to the autolathe. You can see here autolathe execute recipe. So you can just say, hey autolathe, I want to execute the recipe, that's this opcode, and I want to execute it up to 255 times, because that's the amount of values that a byte can hold. I mean the highest value. It can hold 256 values, but the lowest value it can hold is 0, and they stuck with the original meaning of a number. 0 means none, 1 means 1. Therefore you can produce 255 at the max. And the prefab hash. So you can say produce iron sheets 10 go. If you write that into its memory, it will just start printing. You can also say eject all reagents, like when you flip the lever. Or you can say eject only the gold. That's also possible. But let's deal with the logic sorter now. The logic sorter only has one connection, so data and power are combined. And when you toss something in, it comes out straight. So now it should be going in circles. It doesn't. So now it's going round and round. And now we want to program this thing to make a decision based upon what's coming in. So let's put something else in then. Nice storage system, by the way. If you put a silo in between that you open constantly, you can make this loop very, very long in quotation marks. So again, we're not looking at the logic. What's happening? Man, could they fix the scroll bar here, please? We're not looking at the logic values. We're looking at the internal memory that this thing has and that can hold statements. For example, filter prefab hash equals means if the prefab hash, which is of course it is the type name hashed, or just the hash number itself. If that is equal to whatever number we put here, then that will be filtered. And I assume that means it will be pushed to the other side. And here we can just say the opposite. This is not equal. So anything but this thing would be filtered to the other side. Let's filter out the steel. So you can see here we are using individual bits. It is not as complicated as it sounds. The binary system is just a number system. See, when you are writing a number 0.01 or 10 or 17, what you're writing is not really a number. What you're writing is a value. And how that value is expressed depends on the numeric system. We humans, as we have 10 fingers and 10 toes, resorted to the decimal system, which means we have 10 digits to express something. But there's also the binary system that computers use, 0 and 1. And there's also octal, or whatever you want to make up. Hexadecimal, very important in the computer realm, but ultimately the computer thinks in binary. And it has become convention to write binary numbers just like we write decimal numbers. On the very right, there's the least significant number, so if you change that, the overall value changes little. And on the left side would be the most significant bits. If you change those, the number changes a lot. So Then we need to know that bit 0 is the one on the very right, the least significant bit, and bit 63, or however wide our overall number is. In Stationeers we have 64 bits, which is normal for computers these days. That is the most significant bit. So what it is saying here is these bits are not used. These bits tell us which thing we want to filter, and these bits tell the machine what it is that we want to do. This is the opcode, the operation code, 1, 2, 3. Here I'm saying, I will say use this one. This is opcode 1. So we need to mix these bits together, and that's rather simple once you know how. Let's copy the steel ingot's name. There, now we have the steel ingot's name in the hashed form in register R0. So now all the 64 bits are occupied by this number. This number doesn't use that many bits, but when you write such a value, it will overwrite all bits. The maximum amount of bits that the prefab hash can use is 32, which is convenient since in here it can only also use maximum of 32 bits. But we are starting at bit 0 up to bit 31. We need it at bit 8 to bit 39. So what we need to do is we need to shift it to the left 8 times. And we can actually use the help to find out how. Shift. Since it's a bit complicated to explain, let's just remember we need to use the logical shift. We just want to use SLL to shift to the left. There's also SRL, but we will not need this for these kinds of machine programming operations. There, that's simple. Write into this register the result of this register's bits shifted to the left 8 times. So overall I'm just shifting them to the left 8 times in this register. Now the opcode, which is just 1, but then this makes it clear what's happening. We can alternatively also write some comments here or in an empty line. But if the line itself is already explaining this, in programming you should generally avoid to write comments if they are not necessary, because the comments then become a burden that you have to keep carrying around. You have to adjust them, correct them, because if a comment becomes misinforming, then it is destructive and your overall comment reliability breaks down. So you want your comments to always be correct, so you want your comments to be as minimal as reasonably possible. This though is wrong. What's happening here is I'm overwriting the entire register with this value. What I need to do instead is this. What I'm doing here is I'm mixing the bits. If a bit is 0, then it will stay 0. If both, I'm mixing this value and that value together. If both values have a 0 bit in a place, the outcome will be a 0 bit. But if either of them or both of them are 1, then the bit will be 1. So we are just painting into that, so to speak. This mixes the values together. So now we should have the prefab hash of the steel ingot in here in the right bits, and here in the right bits we should have the opcode. A device's memory in Stationeers is called the stack. Just like the chip, for example, also has a stack. We didn't deal with that yet. And SP is the stack pointer. Anyway, in these devices we also have a stack, and we can clear that stack. Here we would say CLR D0 when it is addressed by screws, or here we say CLR D and then the reference ID of the device. We don't have the possibility to use that with batch and naming and such. That doesn't exist. Lucky for us, the devices have their reference ID right on their sleeve. You can just read them out with logic. Here, reference ID. So I can use the LBN batch statement to read into register R1 from the sorter, the one that we care about, the reference ID. So that I can then clear the memory. Not really necessary in our case, but let's just do this. And by the way, it doesn't really make sense to have that as a loop the whole time, but I don't care. It won't hurt. Let's just keep it like this. And then I say put D, which puts that stuff into the memory of the chip at this address. This value will be put there, and this is the target address, and this is the device. Put D. ID number, address, value, which means that now something should be happening to our steel. And there it is. The steel was just sorted out. So I just commented out that put D command. Now it's useful that this thing is running in a loop. I can put the steel back in. And round it goes. Let's try that with the gold ore then. And there it is, sorted out. You no longer need the heinous crime that is the sorter motherboard. Now I want to show you another branching command, which is very neat. You will probably use it often. Why did this just happen? There are many ways to make this happen, you know them already, but there's another one here. This is our code from before. But down here, here I'm clearing the stack of the device, and here I'm loading whether the door is open. And here I'm writing the value to the device, that it shall toss out the gold. But before that, I have this command, branch. And this branches equal to 0. If R2, whether the door is open, is equal to 0, we branch relatively, by 2 lines, 1, 2. So it never makes sense to put a 1 here, because whether this is true or false, the statement, the next line will always be executed. But this means that we will branch down here, even if there's nothing. We can even branch backwards. For the next part, we'll need sound, so I put some gas in here. Let's turn off this annoyance. Here I'm saying not filter prefab hash equals. I just changed it to not equals, and then I chose a hash that is probably not an existing thing. In other words, everything that is not this not existing thing will be sorted out once I open the door, and then there will be silence. Alright. So, the IC housing. What happens if we program something that doesn't make sense? Something as minor, for example, as misspelling, upper lowercase matters, you know? Oh, what's that? Oh, right there. Error, incorrect variable at line 22. 22 is saying jump start. Start doesn't exist. Incorrect variable. Fixed. So now when you point here at the housing, you see 1. Now 0. Now 1. How can we show a number on this thing? By saying, write the setting value of the housing. I'm putting R2, which is whether the door is open, in there. And you don't say SD0 or SD1 or SB a type or SBN a type in a name, but you say SDB, which is always the device in which the chip is housed. So this thing also has logic values. Lots of them. The filtration unit has many. Can we address them directly by using DB? Exactly. Let's do this. First we select the other thing. Import, and then we will close the lid. SDB, the housing, open 0. Nothing's happening because it's off. The program is not running, and now it is. And as per usual, the device is running because that's what happens by default when you build it. What if we want this thing to stop if there's no more gas in this pipe? Pressure differential 0 Pascal. Huh. Shouldn't it processed input go to 0 now? Anyway, there's nothing in this pipe. And now there's something in this pipe. This thing shall react to that. And that's very easy. We just go to the logic values of this thing. And then we can see here. This value, for example, oh, we cannot actually copy this? That is dumb, because it's not written completely. Anyway, apart from all this ratio, nitrogen input, nitrogen temperature output, we also have temperature and pressure for the input side, for the output side, or for the output 2 side. So all I have to do is get the pressure from the device in which the chip is housed, pressure input, into R0. Then say if R0 is greater than 0, that is true. And so now we have a pressure value no longer, but instead a value of 0 or 1. And then I just write this into the mode. Okay, what's happening right now is this thing pumps the pipe empty, then the pipe is empty, it turns off, more air can stream into this. That's a bit dumb, but anyway, for demonstration purposes it's good enough. Now it's off. I mean, if you don't have the sound high enough, then you can't hear it, but it's happening. What if we fail? What if you do something wrong? Then it flashes an error. Oh, it even says what? Incorrect variable at line 8. Okay, so there you have it. Programming in Stationeers. There's probably more to be said, but this should get you very far. Oh, one thing more. There's a select statement which allows you to select a value into your target register based upon whether another register is true or false. So you can, for example, select whether you're currently having a smart canister or one of the small standard canisters in a canister holder, and depending on that logic value you select like 19,500 here or 9,500 there. You can round values to the nearest integer. You can just get a random number from 0 to excluding 1. You can flip all the bits in a value, which is also a way to invert a 0 to 1 or 1 to 0. But the SEQZ approach is more safe. Then you can multiply values. You can take the higher of two values or the smaller of two values. The jump statement also exists in relative form. Jump relative to would mean next, no, the second to next line. And what the fuck is this? It sets the device on fire. Error, chip catching fire at line 3. So, under the right circumstances, that can be rather disastrous, and with this I say goodbye.